Today, I'd just like to talk briefly about a topic that serves as the prelude into what we're going to finish this chapter up on curvature. I want to go back and think in the Calculus 1 context. We will have the graph of some function, y equal f of x, and I want to think about the relationship between the derivative and the angle of inclination of this particular curve. Given a point on the curve, I can calculate its derivative, f prime, at that point. This tells me the slope of the tangent line. F prime at x is the slope of this tangent line, which means literally if I take 2 points on the tangent line and I find out how much the x changes as opposed to how much the y changes on the tangent line, the delta y divided by delta x must be the derivative of f at the x value that we're talking about. On the other hand, I can also think about the angle that the tangent line makes with the positive horizontal direction. Calling that angle of inclination theta, drawing the right triangle, it's clear that tangent of theta is opposite divided by adjacent, which is delta y over delta x, which is the same as delta y over delta x, which is the same as f prime at x. So tangent of theta is equal to f prime at x. As I move around on the curve, the steepness of the tangent line changes. Theta will also change as we move around. I'd like to look into the issue of how quickly does the theta change as I change position on the curve. Initially, I'll just describe everything in terms of the x-coordinate, but then we'll have a refinement. Theta is some function of position on the curve. Dy dx is as well. So this statement says that one function equals another function. I'm going to differentiate both sides of this with respect to x. The derivative of the tangent is secant squared, so according to the chain rule, the derivative of tangent theta is secant squared theta times the derivative of theta with respect to x. This must equal the derivative of dy dx, which is the second derivative of y. We have a trig identity that says secant squared is 1 plus tangent squared, so I'll put that in as well, because I know that tangent of theta is dy dx. This tells me that the rate of change of the angle of inclination with respect to x is the second derivative of y divided by 1 plus the square of the first derivative. In a certain sense, this tells me what I wanted to know, the rate of change of direction of the curve, but it's in terms of x, and many people feel that it would be better to express this in terms of some more physically significant quantity. People usually like to express this in terms of the arc length along the curve instead of the variable x. Because of the chain rule, d theta dx is d theta ds multiplied by ds dx. But since the arc length is the integral of the square root of 1 plus y prime squared, The derivative of s with respect to x must be that radical quantity. Dividing by that radical quantity, we can get d theta ds by itself. This gives me the rate of change of the direction of the curve, the rate of change of the angle of inclination, with respect to the amount of distance that I've traveled along the curve. D theta ds is often given a special name. It's called the curvature. People usually use a capital letter K for this quantity, not to be confused with the vector of length 1 that points in the positive z direction. K for curvature comes from the word krumung. So in the case where y is given as a function of x, as it often is in Calculus 1, we now know how to calculate the curvature, or krumung, of the curve. Along the curve y equals x squared, if I want to know the rate at which the angle defining the direction of the curve changes per unit of length traveled, it's perfectly straightforward to figure out that it is 2 divided by the 3/2 power of 1 plus 4x squared. One way to calculate the curvature would be to solve x squared plus y squared equals b squared for y in terms of x. That turns out to be pretty messy, though. So what I'm going to do instead is I'm going to use implicit differentiation. If x is the independent variable, the derivative of x squared is 2x. Y is a function of x, so the derivative of y squared is 2 times y times the derivative of y, and the derivative of a constant is 0. Divide the 2 out, and I find out that x plus y times y prime must be 0. Differentiate again. The derivative of x is 1. I have to use the product rule on this. It's the derivative of y times y prime, that'll be the y prime squared, plus y times the derivative of y prime, y double prime. Derivative of 0 is 0. So this tells me that the second derivative must be negative 1 over y multiplied by 1 plus y prime squared. The curvature is this second derivative divided by the 3/2 power of 1 plus y prime squared. The curvature must be negative 1 over y times radical 1 plus y prime squared. Let's assume that I'm looking at the top half of the circle so that the y-coordinate is positive. That means that y is equal to the square root of y squared. Otherwise, y would be the negative of the square root of y squared. This looks as though I'm making it more complicated than it actually is, but in reality, this is very nice. Returning to this equation, this says that y times y prime is the negative of the x-coordinate. So here I have the square of y times y prime. I'll be squaring negative x. I'll be squaring x. Assuming that the y-coordinate is positive, the curvature will be negative 1 over radical y squared plus x squared, but x squared plus y squared is the radius of the circle squared. The radius is positive. The square root of b squared will just be b then. If I am looking at the top half of the circle, the rate at which the angle changes with respect to arc length is negative, and it is, in fact, the negative of 1 over the radius. To see this visually, the top half of the circle, when x is negative, will be sloping upwards. As you move to the right, it slopes less upwards. The angle has decreased. Eventually, it begins sloping downwards so that the theta has decreased from being positive to negative, and then decreases further as you move to the right. If we had been looking at the bottom of the circle instead, y would have been the negative of radical y squared, and the curvature would have worked out to be positive. It would have worked out to be 1 over b in that case. In either case, except for a plus or minus sign, the curvature of a circle, as we've calculated it, is the reciprocal of the radius of the circle. This will appear again in some upcoming work. This has been a brief discussion of curvature in the y equals f of x case. The reason I bring this up at this point is that soon we'll be looking at curvature of vector-valued functions, and I want to compare what we get from the logic there to what we obtained here. In the meantime, I hope everybody's having a good day. I'll talk to you again soon.